Okay, so I have started the recording, and I will start with the question that was posed by Urjita last time, and I will clear that. And another point was made by, I think Shivam made a point, Shivam, about one mistake that was in the slide. So I will point that out also. And if you have any questions or doubts apart from all this, then you can raise your hand after that. So I will begin by sharing my screen. So I hope you can see my whiteboard here. Can you
Yes,
confirm
sir.
whether? Yeah.
Yes.
Okay, fine. So you see that, where did it go? So you can see that here this was the circuit, RLC circuit, where there was a mistake in finding out the transfer function actually. So if you go back to the video, you will see that the final transfer function had a s in the denominator along with this expression. So it had a pole at the origin, but it is not supposed to have it. What actually the mistake happened is this. So the mistake was this, that I forgot to put this s in the numerator when I was evaluating the is by us. So you can see from this expression, which is the dynamical, this is the dynamical equation of the system. So from that we derive this. So it is simply one derivation taken, and from here we are getting this transfer function. So you can very well see that there would be an sus here, but I forgot to put that s while in the lecture video. So for that reason, an extra s came in the denominator of the final transfer function. Okay, so if this s was present, that s would not appear because it would internally get cancelled out, and this is the actual transfer function that you would obtain. So you note this thing down, so that when you are looking at the RLC circuit in the lecture video, in the transfer function this mistake is there. So since we were not so much dealing with the transfer function, I overlooked this actually. But Keshav, I think in the YouTube comment, he was pointing out that there is a mistake in the state space representation, but I again checked it. There is no mistake in that state space representation. So there in the state space representation, sorry, I forgot to put my phone in silent mode.
No problem, sir.
Okay, so you will be able to figure out that there is no mistake in the state space representation, because there what we are assuming as the states are these actually: x2, x1 dot is x2, and x2 is I. So basically what is x1? X1 is integration of I dt. So now you can see in this first equation that your x2 dot is this thing, x2 dot di dt. So if you write x2 dot, then you will get all the terms will come in the right hand side. So you will get minus 1 by lc xi x1. So x1 is this integration I dt, and minus 1 r by l x2. X2 is I, and you are getting this 1 by l u, and x1 dot is x2. So this is what the equation was in the lecture video also. So this is fine. So there is no mistake here. And since y is defined like this, so y would be 1 by c x1, like that.
Okay,
So
sir.
going,
Actually, I thought that you defined x1 as I. That's why I was pointing
yeah,
out
yeah,
that.
yeah, yeah. So I also understood that this, you might have thought that. So that is very commonly one can think like that. Actually, in RLC there is a common perception, but here we define x2 as I and x1 dot as x2. No problem. So the next thing I would like to clear is the doubt that was raised by Urjita. So I was doing something, and yeah, we will look at the green annotations first. Okay. So what I try to do here is this. So I took an integration. So this is a general system dynamics. So I was trying to see if we have a differentiation, if I have a derivative of the input, what would happen. So that was a question that was raised. So what I did, I came to this equation finally by taking an integration. So, and now I applied that idea. So in the block diagram idea, so from uh, when we are deriving state equations from block diagrams, so you might have noted that we are taking the output of the integrators as states, correct? So the output of the integrators are considered as the states. So by utilizing that idea, I also defined this integration u dt as a new variable. Perhaps it is a state variable. I am not directly commenting on that. Suppose it is some variable, and we would have simply v dot equals to u. This equation we will get. And the other thing what we defined, what I defined, this integration y dt I defined as x1 and y as x2. If I define this as this, as x1 and x2 as this, then I am getting this equation, x1 dot equals to x2 obviously, and x2 dot is y dot, and y dot I can write everything in the, take everything in the right hand side. And while taking everything in the right hand side, not only u comes, so don't look at these equations. So not only u comes in the RHS, but also bv comes, right? B into v, and where v dot is u. So this is the state dynamics that I derive by considering x1 this, x2 this, and v as integration of u dt. Okay, so because we have to only keep u and not u dot or integration u, all those things cannot be kept in the state space representation, because ultimately we have to represent in this manner: ax plus b u, only u, y equals to cx plus du, right? So for that reason, what happened, and an extra state got defined here, now you notice one thing, that I had clearly told you that the number of states that we need in order to represent a system in the state space realization is equal to the order of the system. So order of the system here is 2, because that is the maximum derivative of the output. That is the order of the system. However, here you see we have utilized 3 states, so this is the third state. So it is behaving like a state, right? V dot. So you can formulate what is a. So if you consider x1 x2 v as your x, then what would be a? A would be 0 1 0 minus a2 minus a1 b 0 0 0 and B would be 0 1 1. Correct? This would be my A and B. Any doubt here? I hope not. But what we see here is that this last row, all the last row is 0. This is a peculiar case, and I didn't want to stumble upon this fact so quickly in the course at such a beginning few lectures. This will come later on. So what is actually happening here, we need to understand now this fact that we can have minimal realizations and non-minimal realizations. So there are now two new terminologies introduced, minimal and non-minimal. This realization that we derived by taking the states, by defining the states as these, leads to a non-minimal realization. When do we call a realization a non-minimal realization? When your A matrix, not exactly A matrix, but there for the time being you can consider only the A matrix. So if the A matrix has such a row which is getting 0 or which is getting dependent on the other rows of the state matrix, same for column also. So if there is a column which is getting dependent on the other columns, then what happens, the rank of A is basically less than n, the order of A. So the order of A is 3 cross 3 here, but the rank of A is 2, which is less than 3. So if such a case arises, then something happens to this state space realization and it becomes non-minimal. It becomes non-minimal. So what is the meaning of non-minimal? When we find that a state space realization is non-minimal, it means that we have created an extra state which was not at all required to describe the system. So we could have chosen lesser number of states than already chosen in order to represent this system. What those two, so here we have chosen the third state extra, that is very obvious now, because we know that the order is 2 and we have created a third order SPR. So that third state is extra. Which third state is extra? Obviously you can understand here that this state is extra because this is this is contributing to the 0 row, this V. But also you saw that choosing this x1 x2 as y and integration y was not sufficient. That's the reason we had to also choose V. So what we come to realize is that the choice of x1 and x2 is actually a skill. If we had chosen x1 and x2 a bit more judiciously, then with that x1 and x2 we could have formulated a second order SPR itself. But since we were not judicious enough, we were not skilled enough to choose the x1 and x2 wisely, and hence we had to choose another state variable. So we landed upon a non-minimal SPR. Okay, so this is the conclusion that we can make from this exercise. So now,
Sir,
yeah,
sir, so we cannot, matlab, this is not the minimum set of
no,
minimum set of states required. So this is not a what we say state vector.
this is a state vector. This representation is a representation. Of course, this is a representation because this is representing your system. However, this is not a minimal representation.
Sir, it has redundant expression.
Yeah, it has redundant expression, but you are not able to catch that redundancy very well here. At least I was not able to catch. Maybe you are able to catch that redundancy, but I was not able to manipulate between these three states and come to two states only. Okay, readily from these three equations. So sometimes this might happen. So that is what I am trying to say. Sometimes this might happen because of our own inexpertise or our own uh, lack of what I should say, lack of skill in choosing the states. So this is the only the skill of choosing the states which made this problem, gave rise to this problem. So this representation is a valid representation. There is nothing wrong here. However, this is not a minimal expression, minimal representation. You remember from your last course in with me, there were minimal expressions and non-minimal expressions. So similarly, here also there are minimal representations and non-minimal representations. I did not want to go into this thing so early in the course. However, since it came up through the discussion, I am pointing this out to you. We will study about minimal representations in some more detail later on. This is not exactly the condition, but there is some other condition related to it. But for the time being, you can say that. So if this happens, then obviously this becomes non-minimal. But sometimes you will not be able to figure out. You will see that a seems to be of full rank, but still it might be non-minimal. So there is a further stronger condition actually. So if you understand this now, so our conclusion from here is that it is our own uh, um, like own lack of skill, or we have not chosen the states judiciously in order to give rise to a minimal SPR. So let us see how if there is any way of correcting this. So these blue annotations, in these blue annotations, I have chosen the states in a different manner, and it led me to a second order SPR from this same dynamic equation which had u dot as well. Okay, but as you will see, this is not very straightforward. So there requires some looking into the dynamics, understanding what to do in order to get a second order SPR. So keeping the output in mind, I have to change my definition of states. So this is a skill. So this skill you have to develop if you want to derive state space representations directly out of dynamical equations containing derivatives of input, if you want to do that. So when you will be given the next lecture, you will basically try to go through the transfer function route, because that is easier. But transfer function is also limited to LTI systems. So when we would talk about nonlinear systems, then again you have to come back to your skills and come back to your own judicious choice of states. So there no way out. You cannot go through the transfer function route in order to come to the SPR when you are dealing with nonlinear systems. But for linear systems, if you have input derivatives, you can easily go to the transfer function and then come to the SPR, and which is very simple, which today only I will upload the slides of upload the lecture video of that. So, but for the time being, let us just see how we have judiciously taken the states for this same system in order to give rise to a minimal SPR. What we have done, I had chosen x1 as minus a2 integration y dt plus b integration u dt. All of this together. All of this together I have chosen as x1, and x2 I have simply chosen as y. Then what happens if I do an x1 dot? Then I get minus a2u plus bu, and that becomes y is x2 minus a2 x2 plus bu. And what is x2 dot? X2 dot is basically y dot. And now you see I have shifted everything to the RHS, and a2 y dot, that minus a2 y dot plus b integration u dt, minus a2 integration y dt plus b integration u dt together comes in this expression in the RHS, and that I can together write as x1. And then I had a minus a1y, which is minus a1 x2 and a u. So this simplifies my life because I only have two states and no more states needed to be defined, and also I get the output as simply x2. So from here you can see x dot, which is the SPR, simply becomes 0 minus a2, 1 minus a1, that's all. And there are no 0 columns or 0 rows. Obviously there wouldn't be, because we have to have second order SPR. So this is one minimal representation. There can be other minimal representations also. So this arises because of my choice of x1 as this and x2 as this. If I had chosen x1 as something different, then this would change. Even then I could have landed on a minimal expression also, but I may have landed upon a non-minimal expression also. So all this depends on the choice of the states basically. So from here what you need to understand is that the states that we are choosing are rather some virtual constructs. However, their number remains same for minimal expressions, for minimal representations. Their number is always equal to the order of the system. Normally we try to define the states as the internal variables which we can readily identify from the system, but sometimes that does not lead to a SPR straight away, and we have to go through a different route of defining the state variables in some other way, and they may not be any variable which directly represents something very physical about the system, like this variable. This is of course a variable, and it is formed by the internal variables taken together in some way, but this thing together does not represent anything of the system, but it can very well be defined as a state. So this thing you try to keep clear in your mind. States are not necessarily defined, are not necessarily identified with the internal variables of the system. They can be any combination or permutation combination of those variables also. However, the number of state variables that you will define in order to get minimal representation will always be equal to the order of the system. If you are having to define more than that number of variables, you will get a representation, but that representation will be non-minimal. And there are certain disadvantages of non-minimal representations that we will talk about later on. I hope this is clear. If there is any doubt regarding this, you can raise your hand. Let me see. Yeah, so no raising of hand, so I guess this is fine. If there is any other doubt, any other query, you can raise your hand. I hope most of you have gone through the video, though I see not many views in the second video that had been put up, but the most of the content is there in the second video itself. So you should go through the video as soon as it is posted and try to clarify your doubts in the next week. Like this week, you should have clarified these doubts of these videos, because today or day after you will get a set of tutorials and you have to solve the questions. So you should clarify any doubt that you have in order to do that. Because you shouldn't keep them for like if you are thinking that you would look at the tutorial sheet and then ask me the question, then it is not so worthy, because I will again be putting up these slides, new slides, so you will have questions from there also. So you might, and I will give preference to clarify those queries rather than the tutorial queries. And tutorial queries I will also not clarify very directly, because I want you to attempt them. Yeah, so anything else? So if you are not having any queries, that is fine. I just want to highlight one fact here, that you try to observe how how the last course of digital electronics and this course of advanced control system, how they are related in some way, in some abstract level at least. So the digital electronics course was also having these ideas of minimal representation, minimal expressions and non-minimal expressions. Here also you came across minimal representations and non-minimal representations. So there is always this sort of a similarity in most of the technical subjects. You will get these ideas again and again and again. So these are some ideas which you need to develop within yourself. And if you look into the world, or look into other different subjects with these ideas developed, you will be able to grasp them very easily, because there is always a background with you. So you will remember that, yeah, this is how I studied this particular subject, so it looks almost similar. So the main idea remains similar. So the way we approach the subject, the way we try to solve problems, the different theories we gather have somewhere a commonality, and some common thread is there. We must try to appreciate this fact, and that will really make things very interesting. How very different. So digital electronics has almost nothing to do with advanced control systems, though you will find many similarities there. When you are looking at state space realizations and the block diagrams, you might find some resemblance with the mood and the mini diagrams. You might find some resemblance, though they are not exactly the same or something like that. But there are in the mood and melee also we had the notion of states. We had input output and how we relate the input and output through the states. Similarly here also you are having the input and output, but there is states inside, and the input goes to the output through the dynamics of the states. As the states get changed because of inputs, then the output comes out. Same thing happens here. Also you should realize that, yeah, one more thing that we have come across in this course is that there can be several representations of the same system. So the underlying system remains same, though there are several representations of that same system. As we change, so this has not exactly come to you right now, but in today's lecture, the lecture that I will send, you will see this and you will notice this fact. From the same transfer function, we are going to derive several representations, and only a few would be shown, and there can be many as you can imagine, perhaps. So it leads to that same fact that we found in the digital electronics course in the very first few lectures, that the same quantity or the value would be represented by so many number systems. When we change the system, the number changes, so the representation changes as we change the system. Here also the same system is there, the same transfer function. However, as we keep on changing the system of representation or the mode of representation, then we get different state space realizations by defining the states in a different manner. And all of them has a relationship between each other, like all the number systems have some relationship between each other, and you can convert from one to another. Here also you will see that the state space realizations can be converted from one to another. So though they are so much different, though they are trying to represent very different quantities, but the way the idea of representation is there, that idea of representation or that philosophy of representing a certain thing, that remains same in both of these. So there is what is underlying these apparently two very different things is that thought or is that philosophy of representing a certain thing, and that remains same. So a level higher in the abstract world, you get this idea of representation, how we represent things, and then we understand that representations can always be different and there would be relationships between the representations. All these ideas remain same even when we are trying to represent very different two very different objects, one being the quantity or the value of something and another being a total entire system behavior, entire system dynamics. So I will leave you with that thought, so you can think about it and perhaps get inspired and get motivated. And so if you don't have any further questions, then I will stop the meeting then. If there are any questions, you want to raise your hand. Okay then. So thanks for joining the session, and you will receive your materials. So always keep checking on Thursdays and Fridays. New materials would be uploaded, and that is the material with which we will carry on the discussion in the next week's classes. And I advise you to send me the queries beforehand, so that that this query which I was not so much comfortable in the live session, during the live session, just after the session ended I had a peaceful mind and I just looked at the problem and it came to me. So if you send me across the query, I can have a look at it and the solution will be revealed probably, and I can share the solution directly during the live session. So it is always better to put across the question beforehand. So thank you for okay, there is a question or something. Khushi does not has the raise hand option in Linux desktop. So this I think she mentioned last time also. Is there any new chat here? So Khushi, if you want to say something, you can unmute yourself. Yeah, I guess no one has to say anything. So okay, then I'm ending the chat and stopping the recording. Thank you for attending the live session.